Hello, everyone. Come on in. Come on in. Come on in. While we're waiting for people to come in, does anybody have any questions before we go ahead and get started? That was definitely not the most intelligent look I've ever made in my face. Oh well. I guess that's why my modeling career never got started. All right. Well, I've exhausted all my sense of humor already, so that's all the funny stuff I got, and it wasn't that funny. Anyways, let's go ahead and get started, folks. We're basically last time I finished off the remaining parts of chapter 7, where I was talking about basically the different types of work. This is going to bring us into chapter 8, and chapter 8 is about conservation of energy. And I wanted to explain to you sort of the big picture, which we'll explain again when I get to this a certain section in 242. But it's kind of nice to see this again, especially if you guys happen to be like taking differential equations or something like that. You'll make some use of this immediately. So what I'm going to do is pull open my uh, iPad and get you started on some information from chapter 8. I'm going to give you a general definition that we can sort of prescriptively use to compute potential energy. So that's going to come in handy. But I'm also going to give you basically this neat little thing or this list of facts where if one of them happens to be true, then all of them are true. So it's kind of nice and cool that way. And it's a very powerful tool in physics in general. So that's what I'm really going to try to bring you. Uh, but before I get started on that, does anybody have any lingering questions about, for instance, stuff that might appear on your exam tonight? I did tell you, for instance, that uh, we are covering basically work and the work energy theorem from chapter 7 in this exam, but it really pretty much is up to you using basically the formula for work equals integral f dot dl, which in a lot of cases is just force times distance times the cosine of the angle between the displacement vector and the force vector. Uh, Using that and using, for instance, that the potential energy is related to the change in work. But that's pretty much it. It's really not too terribly hard. Of course, if you make a plot of force versus distance, then the area under the curve is going to be the work as well. So that's another aspect that you should know for the exams that you're getting ready to take or whatever. But I think everybody knows that. I hope they've gotten it between me telling them and the reading and stuff. They've gotten all that. So let's go ahead. It doesn't look like anybody posted a chat or anything. So I'm going to go ahead and do my share screen. Again, you got a couple more seconds before we start up. So if you have any questions, you can ask them. Okay, so the iPad is firing up as we speak. Hopefully it should be coming on board any minute now. Ah, there it is. Okay, so we got that. Now I'm also going to put up a chat in case you guys don't have a speaker. You can still let me know that you're trying to participate. So with that in mind, let's go ahead. So I wanted to mention to you that last time we did discover something like potential energy. I specifically spoke about a backpack. That might have been last time and the time before it, but your book has an example regarding a backpack. And from it, you see that the work done by the person was basically equivalent to the mass of the backpack times gravitational acceleration times the change in height, where the height went from 0 to some height h, so it's mgh. And what I've just finished hinting at to you is that the change in potential energy, one of the prescriptive definitions you can think of it is that if you're saying there's a potential energy due to a particular force, then you can calculate the work done by that force, and the negative of that work will be equal to the change in potential energy. So that's the first thing I'm going to introduce you guys to. Let's start off with this. I'm going to say change in potential energy, and I'll say sort of defined. So that's why I put a triple equals or triple bars there for the equals. The negative of the work done by the particular force. Okay. So this force right here is supposed to be the force causing the potential energy. So what I mean by that is there's certain forces in nature that for which we can find potential energies. We're going to learn in a second exactly what types of forces those are. And what we're saying is if you calculate the work done in going from point A to point B, by those specific forces that you think are causing the potential energies, then the negative of the work done between A and B will be the change in potential energy between A and B. And remember, change in, like I have written here with the capital delta of the Greek alphabet, which is that triangle, that is always understood to be final minus initial. So if I'm going from A to B, what delta U means would be UB minus UA, because B is the final position and A is the initial position. So if you set that equal to the negative of the work done in going from A to B, then you'll get a definition for the potential energy. So let's start off by showing you what I mean there. I'm going to talk about a gravitational potential energy for a very specific case. So the gravitational potential energy for objects near the Earth's surface. I know that looks bad. Let me fix that real quick. Is found as follows. So what I'm saying is delta U, which is U final minus U initial, is equal to the negative of the work done by gravity. So that's a subscript, not multiplication. And I said near the Earth's surface. What I mean by that is basically the distance between uh, the object you're studying and sea level on the ocean, sea level on the surface of the Earth. That distance between your height and sea level is very small compared to the radius of the Earth. If that's the case, then we can just use the simple formula where a weight is equal to m times g. So what I'm going to do is I am going to imagine a coordinate system. Actually, I'll go ahead and draw a coordinate system for that matter. And let's let this be the x coordinate and this be the y coordinate. And let's say I'm going to start from, whoa, Nelly. I guess I'm just going to randomly erase stuff. That's sort of what I'm going to do. So this is going to say y sub a, and this is x sub a, and it's going to go to x sub b which is going to be y sub b, corresponding to it like this. So the path that we're actually going to imagine is maybe I do like this and then like that. Okay. So that's what I'm actually imagining happening. That little red dot there, which is an object of mass m. Okay. The force of gravity on that object, again, near the Earth's surface. So that implies uh, the distance to the object from the center of the Earth is on the order of magnitude of the radius of the Earth. Okay, so that's another way of putting it. And as long as we have that, then the force due to gravity is going to be W, which is equal to M times G, and it's going to point down. So I can take this definition that delta U is equal to UB minus UA is equal to the negative of the work done by gravity. And again, I'm putting that lowercase g as a subscript to remind you that, hey, I'm talking the force that we're dealing with here is the force due to gravity, but it's in the guise of using the letter g, which is the 9.8 meters per second, so that I don't have to use the whole gravitational GMM over r squared. So in this case, it's going to become the integral from a to b of f dot dl. That's the definition of work. That's what we're supposed to be able to do. So in this case, what I'm going to do is I'm going to imagine that I apply just the right amount of force to allow it to overcome whatever's going on. So in other words, I am going to calculate the work done on this as if only the gravitational force is acting on it. That means I'm going to get a negative integral. The force is going to be in the negative y direction. So I'm going to say it's negative mg, and then I'm going to say it's in the y hat direction. So that's the actual force. I'm going to just choose the positive coordinate direction for my DL, and I'm going to let my range or my limits of integration dictate the direction I'm going. So remember, that's the rule with path and line integrals is you either allow the limits of integration to go from small to large, and then DL points in the direction you're integrating, or you allow the limits of integration to go from your initial point to your final point, and then the DL will point in the positive coordinate direction. In this case, I'm choosing to actually go, because I know I'm going to integrate with respect to y, I'm going to go from YA to YB like that. And I'm just going to choose DY J hat, which points in the positive coordinate direction. I'm choosing that as my DL vector. Okay. So now that I do this, I see the m and the g is in fact a constant, and the negative mg times the negative that's already there is just going to give me a positive mg. And then I'm going to get an integral from ya to yb of, in this case, it's going to be just plain dy. And then I'm going to have a j hat dot j hat. Now, in case you're wondering what happened, how we were able to do this, this dot product is what we call a linear operator. So when I take the dot product of parenthesis dy j hat, uh, I can pull this dy completely out in front of the dot product. That's what I mean when I say it's linear. You can pull out a constant function. You can pull out a variable in front of it. You can also do distribution with pluses and minuses and stuff like that. But in general, what I'm saying is the mg and the dy can be put all the way to the left, and then the dot product just acts between the two vectors. And of course, we know that the dot product, which is another thing that you're supposed to know for this exam, of course, the dot product in magnitude is just equal to the magnitude of the first vector, which all vectors that have the little hat on them, at least in the physics and engineering world, all those vectors are intended to mean unit vectors. And what that means is if you took the x component and squared it, and the y component and squared it, and the z component and squared it, and then added them all up and took the square root, you'd get the magnitude, and that would come out to be exactly 1. Not 1 meter, not 1 Newton, not 1 meter per second, not 1 kilogram, but 1. Okay, so that's what a unit vector is. So when I take the unit vector dotted with a unit vector, the magnitudes are both 1, and these two are identical, so the angle between them is 0. So I'd say times the cosine of 0, which of course all this multiplies to just give you 1. So ultimately, all I get is mg times the integral of dy is just y. So this is going to be yb minus ya. Now, if we want to fit this to make it look like UB minus UA, then I could write MG YB minus MG YA, and then I would get that U, the potential energy, is in fact equal to M times G times Y. And I would tell you that it's completely arbitrary where you put the origin of the XY axis when you do this. And the reason why that's the case is because normally when we're trying to calculate stuff with potential energy, we're calculating the change in potential energy, and that's what matters. So if you happen to have defined your coordinate to be somewhere other than where I put it here, then the difference would be this quantity mgy would be plus c, and this quantity mgya would be plus c as well. So you can see when you subtract them, you would get mgyb plus c minus mgya minus c once that's distributed. And you can see that the c's cancel out. So right now, that's plenty of reason for you to understand that we can put the 0 of the coordinate system arbitrarily anywhere. We'll see another equation later that tells us the same thing, but that's the main thing. Now we have a actual equation for the potential energy, and it's that. And what I'll say is this applies when objects are close to the planet's surface. In other words, their altitude is very small compared to their radius. So we've got that. And I also want to remind you that y equals 0 can be anywhere. So that is a new sort of thing we just introduced. We learned in chapter 7 about work and the work energy theorem. And I showed you the ways you could use that to find out how fast a vehicle is going in a car wreck and stuff like that. But the bigger use is now I'm introducing a particular type of energy called potential energy, which is an energy of position. And I'm giving you a prescriptive definition of how to calculate that. That prescriptive definition is that the change in potential energy is equal to the negative of the work done by the force that causes that potential in going from point A to point B, say. So we got that. Anybody have any questions on that one? Okay, so if we look back at what we had for our spring, for instance, let's do this. Let's imagine that we had a wall right here. There's our wall. And let's imagine that we had a spring like this. And let's say this is the equilibrium position for the spring with a mass on it. Okay. Now I can set up my coordinate system such that that x is there and the origin happens to be right in line with the left edge of the mass. Okay. We know that Hooke's law says the force is equal to negative k times x. And remember, this is the force that the spring applies. So applied by spring. And again, Hooke's law doesn't just apply to springs, but that's easier for us to see. So we use that. In reality, you could say F is equal to negative kx, where it's not a spring, it's just a rod made of some solid material, and you'd still be able to work it out, but the distances would be very small. So I'm going to say, in this case, of course, delta U is equal to the negative of the work done by the spring. So I'll put a little S down there to remind us that it's due to the spring. So what I'm going to do is imagine stretching this spring out a distance X right there so that I'll get something like that. So the spring's been stretched way out there. So what I'm going to get is a negative integral. Now, remember, it's a negative integral of the force applied by the spring. So if I actually stretch this in the positive x direction, which is what I did, then the force the spring is applying is in the negative x direction. So I'm going to say negative k times x, and then I'm going to put an I hat on it. And that negative with the I hat indicates that the force of the spring is in fact acting to the left. Again, I will use the dl to point in the positive coordinate direction. So I'm going to say dx I hat. And now I'm going to choose my range of integration, my limits of integration, to go from the first value to the second value. That will indicate the direction I'm integrating. And the first value is x equals 0, and the last value is x. Okay. Now, I have a negative and then I have another negative. So this is ultimately just going to give me a positive. And of course, the k can come out in front, and I'm going to get the integral from 0 to x of x dx times I hat dot I hat. Again, I hat dot I hat just as 1. And with this in mind, I'm going to get 1/2, because the integral of x is x squared over 2. So now I'm going to get 1/2 of k times x squared minus 0 squared. So this is u, delta u, is equal to u at x minus u at 0. That's the final minus initial notation. Well, that happens to be equal to just 1/2 k x squared. So we can see that the potential energy U at x is in fact 1/2 k x squared. And now we have yet another version of potential energy. So that's the one we already found, but like I said, I just wanted you to think of it now in terms of potential energy. It might make a little bit more sense. And now notice we also get the positive sign that we expected. So anybody have any questions on that one? All right. So there's another type of potential energy I would like to show you, and that is the potential energy due to gravity. And this time uh, I'm not simplifying it to where we're just close to, let's say, sea level on planet Earth. I'm actually going to allow it to be quite a bit different. So what I'm going to do is I will first off draw a coordinate system. So this is going to be my x-axis, this is going to be my y-axis, and this is going to be my z-axis. And in fact, I'm going to let that, which turned out terribly, I'm going to draw a circle and let that be let that be my actual Earth. There we go. Now I got it pretty decent. Okay, so what I'm saying here is this right here is the radius of the planet. What I'm going to imagine is being over here at some point, let's call it A. And in fact, there is a vector R1 pointing to it. Now I'm going to imagine that I leave this location and go to this other location, which I'll call position B. And in fact, I'm going to say that this is a vector R. Let's call this one RA instead of R1. And let's call this one RB instead of R2. That'll be a little bit more in line with what diagrams I'm doing. Okay. Now, what I would like to do is work out what the actual potential energy change is as the negative of the work done by gravity. So in this case, I'm going to say delta U, which should be UB minus UA, should be equal to the negative of the work done by capital G. So notice I just decided to use a subscript capital G because that looks like the constant in Newton's law of gravity. Therefore, it shows you, hey, I'm talking about the more general case. Okay, so it's not multiplied, it's just a subscript. So now what I'm going to do is I'm going to say put a negative in front of that, and now I'm going to integrate. And the force now is, let's say at this particular point, let's say, actually I need a different color. I'm going to do something nice, like let's say right here. There's the vector R at any arbitrary point. Okay. Now, what I want you to understand is that that line, that vector from the origin to the green dot, that is called a radial line. It's called radial because it comes from the origin of, in this case, a circular shape. So we usually don't associate the word radial unless there's something circular about it that we're talking about. So in this case, I'm talking about the spherical Earth centered on the center of the Earth. Therefore, any line that comes back to the origin along that line, but pointing away from the origin, is what we call the radial direction. So R is a radial, or let's say radially directed vector. And we already have some symbols that we use in the physics and math and engineering world associated with a radially directed vector. Specifically, there's a unit vector that points radially outward that's just called r hat. So I'm going to make use of that vector. I'm going to say in r hat direction. Okay, so that's really why I'm using the word radial. So gravity is always going to pull the object towards the center of the Earth because the Earth is basically a spherically symmetric object. It has some, areas where it's a little more dense in some areas than others. So it might not be purely spherically symmetric, but it's close enough for us. Okay. With that in mind, that I know the gravitational force will actually point radially inward. So I want a negative r hat direction. So I'm going to put a negative in front of Newton's law of gravity. And then I'm going to write G and then M for the mass of the planet. and then lowercase m for the object that's moving from A to B, and then all that's going to be divided by r squared, and then times r hat, and that gives me not only the force, but the direction of the force. So notice the r hat would generally be the direction, but I got a negative in front of it, so it's going to point radially inward, which is exactly what we expect. I can again use the positive coordinate direction for my DL. So in this case, I'm going to say my DL is in fact dr r hat. And then the dot product is that thing that's going on there, which really got ugly all of a sudden. So there's our dot product. And the same thing's going to happen that happened before with the dot product. It's a linear operator. This negative and this negative is going to work out to be a positive. So I've got a positive right here. I know that the constant G, M, and little m are constant, so I can pull them out in front. And now I'm going to integrate dr over r squared r hat dot r hat, which again gives us just one. I love that r hat dot r hat with the little curly bracket under it. It makes it, to me, it looks like a drunk owl. I don't know why, but that's what I do. Okay. So as we do with our line integrals, we always express the direction we're going either with the limits of integration or with the DL. I've chosen to do the limits of integration again, so I'm going to say it's going to integrate from distance R1 to distance R2. Notice I'm writing the R without the vector symbol over it. So I just mean the magnitudes of R1 and R2. Okay. Any questions on that part? All right. Well, the integral of r to the negative 2 is negative 1 over r. So I'm going to get yet another negative, and it's going to be g times m times little m. And then all that's going to be multiplied by 1 over r evaluated at r2 minus 1 over r evaluated at r1. Now, dang it, I did say I said I was going to change it to RB and RA, but here I am using the 2 and the 1 again. Let me fix that. Sorry about that. Okay, so the final position is not, oh, I got to fix it up here too. Gosh, when I screw up good, don't I? Oh, it's going to be hard to get in this one. Let's see. Okay. So I'm actually integrating to RB from RA. So this is going to be R sub B, and this is going to be R sub A. Now, if you notice, I really want the B parameter to be the first one because that's supposed to be final minus initial. And I do have that. And all I got to do to make sure that that's the case is I write this as two separate terms. And the terms will be negative G M M over RB minus negative G M M over RA, like that. Okay. Notice the minus minus makes it a positive, which is the same thing that happens when the minus out in front of the GMM hits the minus with the RA. Similarly, notice the minus out in front of the GMM stays on the 1 over RB term. So this ultimately gives us something else, the potential energy, and I'll subscript this one, capital G, is actually equal to negative G, mass of the planet causing it, mass of the object that you're calculating the energy for, divided by R. That is your potential energy if you're interested in finding out what it will be at any distance R, not just R, not very far from the surface of the Earth. So this is for R being any distance from, I'll say, the center of mass of the planet. Now, I'll put that in quotation marks because it could be an asteroid or something like that. Ah, dang it. To the location of lowercase m. Okay. And the planet is the thing with the big M. And again, I'm going to put it in air quotes so that we know that, oh, Mr. Younger's talking about a planet, but it could be like a moon that has a satellite, or an asteroid that has a satellite, or a satellite that has a satellite that has a satellite that has a satellite, and all that good stuff. So we've gotten quite a few different types of energy here. And in general, what we're ultimately going for is this idea of conservation of energy, which is mostly a scalar project. So stuff we solve with the conservation of energy often just involves scalars, not vectors, and that's a reason to do it. That being said, we now have all these quantities. I'm going to write them right across here. What we found was U. Actually, I don't want to write it in red. What I found was U is equal to mgy. That's one case. And of course, you all should know what the special criteria for that being used is. We also found U was equal to 1/2 k x squared. And of course, you guys should know also under what conditions this one's applicable. And now we found yet another one. And actually, with this one, I think I will put a subscript on it just to remind you guys that it's for dealing with gravity a good distance away. And it has this weird idea that the value is actually a negative. So that's something we need to keep, because it's the one time that I'm going to require you to have a actual negative on one side of what I call my conservation of energy equation, which I'm going to introduce to you in a second. Okay. So those are our three potential energies we've worked on. There can be more, but I also want to point out that we also found the kinetic energy is equal to 1/2 mv squared. Now, you don't necessarily know this right now, but you sort of seen a little bit. If I take and hang a mass on a spring and I let it reach equilibrium, then basically it sits still at some pseudo stretched distance. But if I now take that mass and pull it down an additional 2 centimeters, then according to K, or U equals 1/2 kx squared, the spring being stretched from equilibrium by 2 centimeters now has a mass on it that has a potential energy given by 1/2 kx squared. You're assuming the spring is essentially massless compared to the thing it's holding. So really the potential energy is caused by the spring, but it really is the potential energy of the mass that's been stretched down 2 centimeters. Now, if I let go of that mass, because it's stretched 2 centimeters beyond the equilibrium point, that means the force that the spring is pulling up on it with is bigger than the mg, the weight of the mass. So it's going to yank it up and accelerate it. What's going to happen is it's going to accelerate it, and it's going to go to the equilibrium point. And at that point, it's going to have a kinetic energy equal to 1/2 mv squared, where v is whatever speed it has. That 1/2 mv squared is going to be exactly equal to the amount of potential energy it had down at the bottom. And now the potential energy is zero because the x position is zero. So the 1/2 kx squared becomes zero. Now it's going to pass that equilibrium position because it has this velocity. So it's going to go up and compress the spring to about 2 centimeters because that's how far it was stretched. At that point, the mass is going to come to a stop. Therefore, it has zero kinetic energy, but it now has potential energy 1/2 kx squared. And since it's about the same 2 centimeters, it's the same amount of energy it had when we stretched it. Now the spring will start to push back down. That's going to cause it to speed up and again travel through the equilibrium with that same speed v, so that at equilibrium it's going to have an energy 1/2 mv squared, and then that's going to contribute to the energy that slowly the kinetic energy will disappear, and slowly the potential energy will reappear until 1/2 kx squared is exactly equal to 1/2 mv squared. So that whole process is something we're going to study in chapters 14 and 15. But the neat thing is, whenever you have two types of energy that are 1/2 some number times something squared, like 1/2 kx squared or 1/2 mv squared, anytime you have those two types of energies sloshing back and forth, you're going to have something that behaves like a mass on a spring, which is one of the many reasons we study masses on a spring in physics. Okay. So now that I got that, I'm going to give you what our paradigm is, or what this new philosophy is. And this new philosophy is something that we've discovered mathematically. And what happens here is if any one statement below is true, then all of them will be true. So this is a really big deal. This means, hey, if I can prove one of them, then I automatically get all the results from all of them. So, and this first one's kind of weird. Not everybody lists this as a separate one. I'm doing it. So let's say the force F is conservative. And what I mean by that is basically we're going to learn what conservative forces mean, but basically you're not dissipating any energy and moving from one place to another, and changing this particular type of force. Uh, it's going to be applied at all different positions, but I'm not losing any energy to friction and stuff like that. That's not the clearest definition in the world, but when I show you the rest of this, you'll have an understanding of how to figure it out. Okay. So the force F is conservative. Like I said, some books choose not to say this is a separate one. And then they'd say this one right here is the first one. I sort of look at this as the definition of the first one. But basically, there exists this little operator that we call the gradient operator. And basically, what it is an upside down Greek letter delta. And that particular guy, if I take a cross product of it with the force F, and I get, notice I wrote 3 equals bars there, or 3 bars there for the equals. That in this case, I'm using it to mean identical. That is all going to be equal to the 0 vector. Okay. I'll show you what that means, how to calculate that sort of stuff in a second. But I want you to say, this is also saying the curl R rotation of F is identically zero. Okay. What I mean by identically is when you do this computation, you might have X's and Y's and Z's in there, or you might have R's and thetas and phi's, or R's and thetas and Z's in there. What I'm saying is no matter what R theta phi or R theta Z or XYZ are, the answer is going to be 0, period. Okay. You don't have to choose a specific XYZ to make it zero. It's going to be zero for all cases. So that's one of the rules. Another one of the rules is that the integral from, let's say, A to B of f dot dl is actually equal to some other function, f of b minus that same function again, but f of a. And this means is independent of the path taken. In other words, what I'm saying is the work done in going from point A to point B doesn't matter what path you take. Every path should give you the same answer, and every path is going to give you an answer that is some function evaluated at the final minus some function evaluated at the initial. Okay, that's a big thing. Now I'm going to do 4, and this one's a little bit different in that I'm going to introduce a new symbol. Notice I drew an integral with a circle on it. When you draw an integral with a circle on it, that's a reminder that, hey, this integral is supposed to be conducted over a closed loop. So it doesn't mean it has to be a circle or anything. It just means you have to start and stop on the exact same spot in space. So in this case, it's going to be f dot dl. And I think you can see that the answer is going to be just plain 0. Because if the top one's true, then the fact that you got a circle on the integral means that the initial position and the final position are like both A or both B. So you'd get f of B minus f of B, which is 0, or you get f of A minus f of A, which is also 0. So that's another thing that's useful. And now, number 5, here's some fancy mathematics symbols that comes in handy from time to time. If you write the E upside down and backwards, that means there exists a scalar function let's say U. Now here's another mathematical symbol. It's that one right there, and that means such that because it looks like a cursive ST. See, it looks like that. Such that the force is equal to the negative gradient of the potential. Okay, so now let me go ahead and explain what this is. So the whole reason that we were able to find these scalar potentials, the mgy, the 1/2 kx squared, and the negative gmm over r, the whole reason we were able to find those is because the gravitational force and Hooke's law force are conservative forces. And they're conservative forces because their curl is 0 or their rotation is 0. And therefore, all of these things are true, including number 5, which says, hey, you can find a scalar potential U. And if you need the force, all you got to do is let that little gradient operator operate on it and then multiply it by -1, and out will pop the force vector. Okay. So now let me show you what the actual nabla slash gradient slash del is. Okay. So this triangle thingy, that is a vector operator, and I often will write it with a little line right here beside it just to remind you, hey, this is supposed to operate on something to its right. So when you stick something there, it actually does something to whatever's to its right. I'm also going to leave spaces as I write what this is, and the spaces I'm going to leave are for you to put in whatever you put to the right of the symbol. So if I'm doing this in, for instance, Cartesian coordinates, then I'm going to take I hat, and then I'm going to do something that's called a partial derivative, which if you haven't had uh, all of Calc 2 usually, and sometimes it's not even covered even then, but definitely if you've had Calc 3, you should know what this is. It's a partial derivative, and all it is a derivative where you pretend all the other variables are constants. So we write it like a backward 6, and I'll put an X in the bottom because that's the one for that. Notice I'm going to leave a space. In that space would go whatever's in that underline that I left to the left. Now I have a J hat, and that's going to be a partial with respect to Y because that's the Y variable. Again, I'll leave a space, and then I'll have a K hat partial with respect to Z. So again, you can see there's a space to the left of it, or excuse me, to the right of the actual operation. Now, if I wanted to calculate, for instance, the curl, then what we have to do is we say del cross F is equal to the determinant of a matrix. And that matrix has its top row given by I hat, J hat, and K hat. So I'm only giving it to you in Cartesian coordinates. It's quite a bear to work out the mathematics of all the other stuff that happens with this. Now I'll take as my second row is going to be the first vector, that nabla vector or that del vector. I'm sorry, I keep throwing the word nabla in there. I'm one of the weirdos that had a teacher once that told me that in Portuguese, the symbol gradient that I use is called nabla. So I'm stuck with that, and I keep saying it all the time. So I apologize, but that's what it is in Portuguese. So one easy way of writing this, instead of writing the whole fraction, I can just write the backward 6 with the X, the backward 6 with the Y, and the backward 6 with the Z. And then I got to write the third vector's components. I got to write that in the third row, and that's going to be the X component of F, the Y component of F, and the Z component of F. Now, we are going to learn a cross product later, and this is actually a cross product that we're doing. So this will actually help you later anyway. So I'm going to go ahead and show you what we do. Uh, what we do is you can expand on minors. That's one of the wording terminologies you'll run into, and usually like it'd be algebra 2 or college algebra or something like that. But what we do is we realize that the I hat vector is in the top left corner, and that means it's the first row in the first column. And then we take -1 and raise it to the sum of those. That's 1 plus 1 power. And of course, -1 to the 2 power is just +1. So that means we don't have to do anything special. I don't have to multiply by -1. I'm just going to blindly write down the I hat right here. And now that I've done that, I ignore that column and that row. So I have to ignore the first column, which is the one that has I partial with respect to X and F sub X in it. And I also have to ignore that row, which is the one that has I, J, and K in it. All I have left is this little, oops. All I have left is this little bit of the matrix itself. And that little matrix is a 2 by 2, and we know that the determinant of such a matrix is multiply top left by bottom right and then subtract from it the top right by bottom left. So I'm going to compute that now, and what's going to happen is I'm going to take the partial with respect to Y of the Z component of F minus the partial with respect to Z of the Y component of F. So that's the first term. Now I'm going to expand upon J. Now J has the first row, but it has the second column. So this time I'm going to get a -1 to the 1 plus 2, that's the 3 power. That's going to give me a negative. So the way I remedy that is I could just multiply by -1 and do my thing, but I found it convenient to actually just compute the determinant of the remaining matrix in the opposite order. So I'm going to go ahead and write down j hat. And now that I've used j hat, that means the only part of the matrix I have left would be the partial x, the fx, and the partial z and the fz. In other words, I have to leave that middle column alone, and I have to leave that top row alone. But since the j is supposed to be negative, I'm going to do it in the opposite order. So I'm going to take the partial with respect to z of f sub x minus the partial with respect to x of f sub z. And then finally, I'm going to expand on the k hat vector as well. Notice the k hat vector has 1 comma 3. 1 plus 3 is 4, so we're going to get a positive again. So all I have to do is just do the normal determinant. So in this case, it's going to become the derivative with respect to x of f sub y minus the derivative with respect to y of f sub x. And that's the whole curl. So del cross f is defined to be the curl of f, or another word they use is the rotation of f. And it really is a rotation. So for instance, if you took the velocity field of water in a bathtub or a sink, what you'd see is when you first open up the drain in the sink or the bathtub, water's going to curl around it and then spiral into the insides. That curling around it is an indication that it has a curl. Now, if you got to the end, or if it was very shallow from the get-go, when you pulled the cork so that it would drain, then water could in principle come straight towards the middle of the drain. In that case, it wouldn't have any rotation. It would have all convergence, where all the water velocity vectors are converging at one point, and it'd have another vector operation called the divergence, and that would come out like negative. So that's what this is. If you want to see why mg worked and gave us a scalar potential mgy, then you can just do this. Let's say example. Okay, so we're going to say the determinant of I hat, j hat, k hat, and then partial x, partial y, partial z. And then in this case, we're talking about a force acting in the y direction. That's the gravitational force. And in fact, it's going to have no x component, so that's going to be a 0. It's going to have a y component that's negative mg, and then it's going to have no z component. So you can automatically see that looking at the formula I had before, since fz and fx are 0, you're going to get a lot of stuff canceling out. In fact, I can write it down. This I hat is going to be partial sub y of 0 minus the partial sub z of negative mg, which is also 0, plus j hat. That's going to be partial sub z of 0 minus the partial sub x of 0, like that. And then the k hat term is going to be partial sub x of negative mg minus the partial sub y of 0. And the main thing is all that equals 0. In other words, it's 0 I hat, 0 j hat, 0 k hat, and that shows you the curl is 0. That's why we can have the U equal to mgy. You can also do it with the gmm over r squared, but in that case, you have to actually render it in coordinates that are like spherical coordinates as opposed to cylindrical. So that's why I didn't do it. There is another operation called the divergence. And that divergence would actually be I hat, or excuse me, not I hat, because it's a dot product. It's just the partial of f sub x with respect to x plus the partial of f sub y with respect to y plus the partial of f sub z with respect to z. So that's another operation you could do as well. The gradient operator, the del, can actually also operate on a scalar, and that's what we're doing in the line above. So what I'm going to say is del f is equal to I hat partial of f with respect to x plus j hat partial of f with respect to y plus k hat partial of f with respect to z. So that's just some other stuff that will come in handy. I will tell you that there's also another thing. If you've covered exact differential equations in your differential equations class, you'll know that such differential equations are sort of seen as if they're coming from a bigger function that you can't see when you see the differential equation. So for instance, you might have something like 3x squared dx plus 3x squared y dy equals 0. And when you have such a differential equation, what you do is you take the partial of 3x squared with respect to y. And of course, there's no y in there at all. So this is just like the derivative of a constant. So I get a 0. And then you take the derivative of 3x squared y with respect to x. Notice I did an opposite variable than they're being multiplied by. In this case, the derivative of this with respect to x, you just pretend like the 3, which is a constant, is a constant. The y is a constant. Maybe it's like a 4. And then you take the derivative of x squared, which would be 2x. So the 2 times the 3 gets you 6x. But then the y is like a 4, so you have to leave that there as well. Okay. So when you're doing this type of differential equation, if you found these two functions equal to each other, then you know it's exact. This is not an exact one. But the reason why that matters is because there's a certain case in which df is equal to the partial of f with respect to x dx plus the partial of f with respect to y dy. You could actually go a third variable too if you wanted, but we normally just do the two variables. But the main thing is the functions that behave like this create exact differential equations, and they are somewhat related to those 5 rules. I will tell you that I haven't looked up the precise wording of it. That's why I'm not giving it to you. But I'll just tell you that when you start doing like steam table or engineering thermodynamics, the large majority of engineering thermodynamics or thermodynamics in general would just be taking a buttload of derivatives. And the reason why is there's many functions that are like this f here that I'm pretending exists, where you can take the derivative of it with respect to x and multiply it by dx, and take the derivative of it with respect to y and multiply that by dy, add them up, and that actually gives you the change in f if the x and the dx change by dx and dy. So that's all about thermodynamics and stuff like that. So hopefully that gives you a little bit of a feeling for what's going on. I know I didn't show you very much there, and that's mainly because I haven't thoroughly updated my knowledge base to include that part about the differential equations so that I could write it down in a written form that's good and right. So I just wanted to share it with you so you know that it has some tie-in, but that I didn't give you the details on it. All right. So all of that is basically the neat new thing. And the neat new thing basically says that, hey, you can conserve energy. And most of the time, most authors will use this. They'll say delta U plus delta K is equal to 0. And this is called conservation of energy. Actually, it's conservation of mechanical energy. But this is only for conservative forces. So if we have a dissipative force like a friction force, a air resistance, or something like that, you can't use it. There's other ways where you could try to employ it, but it's not that easy. What I like to do is this, though. So my way, I I basically assume all terms are positive, and then I say except, this is what I was hinting at earlier, except for that guy. Okay. So what I do is I write work in plus potential energy initial plus kinetic energy initial is equal to work out plus potential energy final plus kinetic energy final plus E loss. Okay. And this is my version of conservation of energy. And it's not really just conservation of energy. By adding the work in term and the work out term and the E loss term, that gives me 3 spots where I can take in certain types of energy. Okay. So, and actually I should really, let's see if I can do this real quick. Oh, that did not work as well as I had hoped. Okay, that's better there. Okay, that's good enough. All right, so all these terms have to be positive, so you got to keep that in mind. Then you're just working for the magnitudes of the forces and stuff like that. So it looks like we got 10 minutes. That's probably a decent amount of time for me to work one big problem that takes all this into account. So what I'm going to do is say example. So what I'm going to do is I'm going to have a level surface and then a steep incline. And then I'm going to run into a rough surface. That extends for 50 meters, like that. And then at that point, there's going to be a really friendly, helpful, soft, comfortable spring wall in which the surface is perfectly smooth and no friction. So what I'm going to do is say right here, mu is equal to 0.300, and that's mu kinetic. And right here, mu kinetic is equal to 0. And I'm also going to say that this height from here to here is 200 meters. And I'm going to have a little sled here. And I'm going to have me pushing on it like this. Okay. So I'm going to put in Okay. Now the questions I want to ask are A, how fast at end of the push? In other words, I pushed you, or I pushed the person on the sled for a distance of 2 meters with a force of 100 newtons. All of that is supposed to be parallel. So I want to calculate with work in what's the final potential or the final kinetic energy, and therefore what's the final speed. I am going to say, by the way, that the mass is equal to 85.0 kilograms. Then part B is how fast when we hit friction. In other words, how fast are we going right here? Oh, and then part C will she cover the 50.0 meters, or how fast? Whoa, Nelly. Okay, so C has two possible outcomes. If I actually go the full 50 meters, then I have to answer how fast it's going when it gets off the 50 meters. Otherwise, the person's going to come to a stop. And then finally, part D, how much compression? In other words, how much am I going to compress that spring? If I actually make it through the friction spot. So those are the problems we're going to work. It's really not as hard as it seems. We've got a good 5 minutes, so that's okay. Let's do this. Part A. So for part A, what I'm going to do is realize that work in is going to be, well, let's actually write it this way. Work in plus U initial plus K initial is equal to work out plus U final plus K final plus E loss. Okay. The key thing when using this equation is you make sure you account for each type of energy and you count it only once. Okay. So what I'm going to do now is I'm going to say there is work put in, but the height that the sled and person are at when I start to push and when I stop pushing is exactly the same. So UI and UF are canceling each other out because they're equal. It's MGY plus minus MGY. In other words, MGY is on both sides. The initial kinetic energy, however, is zero because I'm assuming I'm starting to push the kid on the sled when they have zero speed. I'm not going to get any work out because I'm not compressing any springs. I'm not doing any work against friction. So this one's just going to be zero. I'm not going to have any E loss because I'm pretending that all this snow is perfectly smooth up until I get to that hairy spot. So this part's going to be zero. So all I get is basically 100.0 newtons times 2.00 meters is equal to 1/2 of 85.0 times V squared. So V is going to be equal to, I'm going to take the 200 or the 100 times the 2 meters. That gives me 200, obviously. I'm going to multiply that by 2 to get rid of the 1/2 on the other side. That's going to give me 400. And then I'm going to divide by the 85 kilograms. And that's going to give me basically the quantity equal to V squared. So I'm going to say V squared is equal to 4.706, which implies V is equal to the square root of that, which gives me 2.17 or 2.169 meters per second. Okay, so that's part A. Does that make sense to everyone? Okay, part B is how fast when we hit the friction part. So for part B, what I'm going to do is write, again, work in plus UI plus KI is equal to work out plus U final plus K final plus E loss, like this. Now, in this case, I'm going to start it right after I'm finishing pushing. So I know the initial kinetic energy, it's basically going to be that 100 times 2, because that's what the kinetic energy is. The potential energy, on the other hand, will definitely not be 0, but the work in is going to be 0 for this part. Okay. The work out is going to be 0 for this part because I'm calculating what's the velocity down there where I drew V equals question mark. The final potential energy, since I'm allowed to put the 0 anywhere, I'm going to say U equals 0 right there at that height. And I need to find out what that kinetic energy is equal to, so I'll just leave that blank. But I know that there's no friction here, so I can also put this as 0. So ultimately, all I get is the initial kinetic energy and the initial potential energy. The initial potential energy would be 85.0. I'm going to leave off the units, but notice that's a kilogram times 9.80. That's M times G, again, leaving off the units, times a height of 200 meters. That's the potential energy, plus the kinetic energy, which we already worked out to be 200 joules. And all that's equal to, darn it, all that is equal to 1/2 85.0 times V squared. So I can get, in fact, V is equal to, now in this case, I'm going to say 85 times 9.8 times 200 plus 200, which is 166,800. That's the total energy on the left. That's got to be multiplied by 2 and then divided by 85.0 and then take the square root of it. And yeah, that should be it. So now I'm going to take that, multiply by 2, and divide by 85, and then take the square root of that. That gives me 62.65 meters per second, which is on the order of 168 miles per hour. This is going to be a bad incident. Okay. So that's not the best of answers, but anyways, we got the answer. That's part B. Now, part C wants to know, are we going to be able to make it across the whole 50 meters? I think you can already tell that we are, but really all we need to know to do that is to go on with our conservation of energy. And what I'm going to do is say that my energy when I hit that thing is going to be the whole 166,800. And then I'm going to slowly accumulate some E loss while I defeat my conservation of energy. So I'm going to do with part C, I'm going to have work in plus U initial. If you guys need to split when time's up, go ahead and go. I'm going to finish this on the recording, but I know y'all got an exam, so go for that if you need. I got K initial is equal to work out plus U final. Go ahead and text me or chat me your first and last name too. K final plus E loss. So what I'm doing right now is I'm going to assume that it comes to a stop after some distance with an energy loss, and I'm going to assume that energy loss comes from 50 meters. Therefore, if I actually do get a zero, then I'll know that it didn't make it. So what I'm going to do is I'm going to say 166,800 joules is equal to the workout is going to be zero. The change in potential energy is going to be zero. But what we will have is 1/2. Oh, actually, since we're assuming it comes to a stop, I'm going to assume that the potential energy is zero, or excuse me, the kinetic energy is zero. And therefore that 1/2 will not be there at all. And all I'm going to do is say the E loss is going to be the person's weight, which is 85.0 kilograms is their mass. 9.80 meters per second every second is G. That's the normal force. Now I got to multiply that by 0.300, which is the static coefficient, or excuse me, the kinetic coefficient of friction. And all that's going to be work contributing to the work done, which I'm going to say is some number of meters x. So if I solve for x and x is greater than 50 meters, then I'll know it went too far. And sure enough, 166,800 divided by parenthesis 85 times 9.8 times 0.3, close parenthesis, that gives me about 667 meters. So that's way, way, way bigger than 50.0 meters. So we know it's going to make it all the way to the end. I want, therefore, to find out how fast it's going at the end. So now I'm going to do 166,800 joules is the energy we start off with. Now this is going to be equal to the energy loss in going across the friction plus the decrease in potential or kinetic energy. So that's going to be 1/2 85.0 times v squared, which is what I want to know. Plus, in this case, it'd be 85.0 times 9.80 times 0.300. I think that's what I used for my friction, right? Yeah, 0.300. And then times 50.0 meters. Okay, so 166,800 minus 85 times 9.8 times 0.3 times 50, close parentheses. That gives me 154,305. Way more sig figs than is really relevant. And that's all equal to 1/2 85.0 times v final squared. So if I want to know what the final velocity when I get off of the friction, that's going to be that number 154,305 times 2, and then divided by 85, and that's going to give me 3,630. So I want the square root of 3,630 meters squared per second squared is what the units work out to be. Now I'm going to take the square root of that, and that gives me about 60.2, and that's 60.255 meters per second. So that's how fast it's going at the end of the friction part. Now I want to know how far it compresses that plywood that's padded with a spring. And I meant to write it. I don't think I did. No, I did not. So the spring constant here is 1,000 newtons per meter. So now for part D, I'm just going to see how that works. So part D, I know the energy I have coming in to the plywood with the spring on it is 154,305 joules. That's going to be equal to, in this case, we're actually going to have the kinetic energy go to zero, but what we're ultimately going to have is all of that energy is going to be dissipated by by work out. And the work out in this case is going to be 1/2 times 1,000 newtons per meter times x squared. And x is going to be the square root of 2 times 154,305 joules over 1,000 newtons per meter. So I'm going to say 154,305 times 2. And now I'm going to say divided by 1,000. That gives me 308.61. Over 1,000, or excuse me, that's all of it. Sorry about that. And that gives me 17.57 meters. So not a very realistic problem, but that is the actual compression that would have to happen if that piece of plywood and spring was going to stop this sledder from ratting. So that one example should help everybody be able to figure out how to use all the different terms. I will write on there that that was a workout. That I used there. So you folks are free to go. Thanks for coming, everybody. Anybody have any questions? Feel free to ask them. I'll wait for the last person to leave. Thanks for those of you who did stick around. I'm sorry it took so long.
That's okay. Thank you.
Thank you, Jennifer. Y'all have a good one, everybody. Good luck on your exam. Hopefully I made it nice and somewhat helpful for you.
For the chapter 8 homework, that's not going to be due this Sunday, right? It's going to be due next Sunday since we just started chapter 8.
Yeah, chapter 8 will be due the following Sunday. Chapter 7 will be due this Sunday though.
Okay. All right.
All right.
Hi.
Hello, what's going on, Hannah?
I went to take my practice test this morning that you had reopened for me Monday, but it's
Okay.
closed again.
Oh, that's not good.
So
Let me see. And you are are you taking 241 and 2 right now or just 241?
just 241.
Okay. All right. So let me fix that. You are in the 241, the night section. And it was a practice test for which test?
Chapter 4 through 6.
Okay, gotcha.
So I don't know what
Their practice
happened.
test
I
for
plan
that.
on doing it tonight, so hopefully it'll stay open.
Yeah, that's just my mistake. I said it to 10. I might not have even fix it or whatever. Today is March. Oh, the 13th. Yeah, so I never fixed it. What day do you think you'll finish the test? By Thursday or Friday?
I can finish it tonight. That was my plan to get it done tonight.
Okay, just in case, I'm going to go ahead and make it till Friday.
Okay.
Just in case something goes wrong, I won't have to reset it. There you go. That's fixed now, Hannah.
And since my face-to-face practice tests or my face-to-face tests will not be until Monday, am I able to have the practice test also open until Monday?
Yes. Yeah.
Okay. Are you?
And that's the practice midterm, right?
Yes.
Okay, I'm going to open up your test for until Friday too, just in case anything happens. I'll fix that real quick.
Can you open it until Monday or Sunday night? Since I don't have to take the test until Monday.
Oh, yeah, I'm actually talking about test 4 still, but yeah, I'll do that with the exam.
Okay.
So I just did this for test 4, and it's Hannah Keen, right?
Yes.
Okay. So I've now set that up. Now I'm going to do the practice face-to-face test, which is right here. Okay. And you say you're doing that Monday morning. So I'll set it for you. And that's Hannah Keene.
Yes.
And I'm setting it for you to be Monday morning, the 18th at 9 a.m. And it should disappear Monday morning, the 18th at 9 a.m. as well. Okay, I've got it all set up for you. Sorry about not setting that. I thought I had done it, but I might not have hit save or something. Sometimes there's little buttons you hit, and if you don't do it, nothing happens. So that could be what happened.
Right.
All right, thanks,
Did
Hannah.
you move? It's
Go
still
ahead.
saying my practice midterm is closed
Try
until
backing out
March
of that
14th.
page and then going back on it. Let's double check here.
Did you do put the tests on?
What I'm showing right now is practice tests for.
Okay.
Did it let you back
Yes,
in that time?
midterm at 9 a.m. It updated.
Okay. Yeah. Sometimes it just needs to, get up to speed. But yeah, I think that's it. Okay.
All right. Thank you so much. I
Hey,
plan
if
on
you
working
run
on it
into
over the
that
weekend.
problem again, text me directly because that'll happen in real time, and then but make sure you tell me your name in class. Okay.
Yes.
All right.
Perfect.
See
Will
you,
do.
Hannah. Have a good one.
Thank you. Bye.